Good afternoon. My name is Ahmad Mintabo. The work that I'm going to present is the target adaptive control dual rotor rotational system with unknown geometry and unknown inertia. This work has been done in collaboration with the John Manuel Portela Delegado and Proctor School at the University of Maryland, Baltimore County. As you may know, rotational systems are really common in robotics. In robotics, we are mostly dealing with translational and rotational problems. You can see rotational systems in drones, quadcopters, VTOL system, and robotic arms that we want to control their rotation. So there is a need for precise control, whether it is the stabilization or tracking in rotational systems. Here you can see a simplified test bed of a 1 degree of freedom rotational system that we have developed for an undergrad course, so they can implement different controllers and get familiar to how a control is implemented in real time. But in this one, we want to consider 2 degree of freedom rotational system. We are considering that there are unknowns in the system. The physical parameters like these rotational systems are mostly equipped with brushless DC motors, and the unknown parameters we can mention the rotor, the motor's constant, the moment of inertia, and the length of the arm. These kind of unknown parameters that we mostly see in rotational systems. Here you can see a simplified block diagram of a 2 degree of freedom rotational system. We have two bases attached at the point C, and we have 2 degrees of freedom. So we have one horizontal angle, and the other one is the vertical angle. As you can see, 2 rotors are attached at each point, at each end point, and they are bidirectional brushless DC motors that consider that they can rotate in both directions. You can see how the forces and moments are calculated. That there is a relation for each force. There's a relationship between the speed of rotors and the constant of motors. But in this one, we are considering that the motor constants are unknown. Also, we are considering the rotors to have a different angle with respect to the axis that they are attached. So here we are showing that they are perpendicular to the axis, but in our work we are considering that they can have any arbitrary angle. So if both rotors are pointing toward the vertical direction, this is the control allocation matrix for generating moment in vertical and horizontal direction. You can see with this control allocation matrix, we can generate moments in vertical direction and the horizontal direction. But if we consider an arbitrary angle for the rotors with respect to the axis, this is the control allocation matrix that we get. You can see there are the sines and cosines of beta A and beta B, which are the angle of rotors with respect to their axis and base. So this control allocation matrix becomes singular when rotors are pointing into completely different directions, and we cannot generate arbitrary moments in the vertical and the horizontal direction. And here you can see the determinant of this control allocation matrix. When the sign becomes 0, we lose the controllability. The equations of motion of the system is derived with Euler method. You can see them at the top. We are dealing with 2 differential equations of order 2. So we consider our state vectors to be angles, the angular rate, and our input would be the speed of rotors. So by considering these states, we can write our model in the strict feedback form as shown in the middle. The strict feedback form helps us to easily apply packet setting and IOL control techniques to our system. So So as you can see here, we have two parameter matrices, theta 1 and theta 2. They are unknown, and we want to use adaptive techniques. So with the controller can adapt to variations in these parameters. And the matrices are defined. So F1, F2, and G, as you can see, they are constructed only using the state. But theta 1 and theta 2, these matrices, they have the parameters of our model within them. So the unknowns that we are dealing with them here are the moments of inertia, the length of our rotational system, the constant of rotors, and the angle of rotors with respect to their base. So we want to use the input-output feedback linearization control method. Given a system in the nonlinear control affine form as x dot equal f of x plus g of x u, we have our measurements or output as h of x, and we want to linearize our system with feedback. So we are considering our angles to be as our output, and so we need to take a derivative of them 2 times, and they are going to give us the relative degree of the system. So y1 would be the measurements for the first angle, the angular velocity of it, and y2 would be again the second angle and its angular velocity. And as the relative degree is 4, we don't have any zero dynamics. So by using the nonlinear transformation and getting the virtual control as alpha x plus beta x u, we can linearize the dynamics of the system. And then we are going to deal with the linear system as shown there, p dot equal ad plus bv. So with these terms, alpha and beta, we have cancelled the nonlinearities, and we remain with the linear system, and we need to design a linear controller. So we have the plant here, which is the 2 degree of freedom rotational system, and we linearize it with the oil control framework. And so as you can see here, the controller consists of alpha, beta, and v. So alpha and beta, they are calculated with taking the derivatives of output, and they cancel the nonlinearities. And with V, we design a linear controller. So we can follow a reference trajectory, whether it's like a trajectory or if we want to do the stabilization at a constant angle. So the linear system becomes as shown here, and we design a linear controller V such that the linear system AC plus BCK becomes Herpitz, and we can design a linear controller using LQR or pole placement routine to design our linear controller that helps us to stabilize our linearized system. So as we said, in this work we are considering those physical parameters to be unknown. We are going to use a regression model to help us to estimate the unknown parameters. So the regression model is written in a linear form as y equals phi times theta. Phi is a regressor matrix constructed with the measurements that we have from the states. And theta is the vector of unknowns. So we need to write it in this form. As you can see, we can write phi as shown here, and it is constructed only with the states of the system and also inputs, and there is no element of the unknown parameters. And we also have the theta vector on the right, which is constructed with unknown moments of inertia, the motor parameters, and also the angle of the rotors. So we write them in this form, and based on the equation of motion, it becomes the equation shown in the middle. So we need to filter both sides, and the reason that we are filtering the regressor is for noise attenuation, because in the measurements we have noise, and also as you can see we have T2 dot, which is the derivative of our state, and when taking the derivative in practice it makes problems because the derivative term and taking derivatives causes like a high frequency noises in our system. So we filter them with a low pass filter. It's strictly a proper low pass filter, and we get the filtered signals as P of F and P of F. So after getting the filtered signals, we use this finite time convergent estimator that gives us an update law for the unknown parameters. So first we low pass filter the data that we have, which are the states of the system and the regressor matrix, and we feed them to the finite time convergent estimator to give us update law. And as you can see here, we have the final control law. The controller was designed with IOL technique, and the estimates are getting updated by the finite time convergent estimator, and this control law allows us for stabilization and trajectory tracking of our rotational system. So we did some simulation results. First, we considered the step command tracking. We are initializing our rotational system from 0 angles, and we wanted to follow unit step command in each angle, the horizontal angle, the vertical angle. You can also see the control inputs, which are the velocity of the rotors. Also, the figure on the right is showing the parameter estimates and how they evolve through time. Then we do harmonic command tracking, which we want to follow a harmonic angle on both the horizontal and the vertical axis. You can also see the control inputs and how the parameter estimates evolve over time. Then we did a robustness and a sensitivity test, so we want to see how the technique is robust to variations. We scaled the moment of inertia by scaling factors that you can see here, and in each case the algorithm, the controller was able to stabilize the system. And then we did some variations in the angle of rotors with respect to the base. We changed them, as you can see, from pi over 8 to pi over pi over 3. And each case, again, the rotational system is able to establish itself, and there is only some changes in the control signals based on the changes that we had in those variations. And finally, we scaled the rotors constants, and as you can see here, from a range of scaling factor that again we want to establish the rotational system, and it's able to follow the unit step command even with varying the rotors constants. So in conclusion, we derived a mathematical model for a 2-degree of freedom rotational system, assuming unknown geometry of the rotors, the variation in the angle with respect to the base. We designed a nonlinear controller and also adaptation for adapting to the unknown parameters, and we validated it through simulations. We did also some robustness assessments to see how the controller is robust to variations in unknown parameters. Some limitations in the work is that we consider that to represent the attitude with Euler angles, and it has singularities. So in our future work, we want to use other attitude representations, and finally design the 2-degree of freedom rotational systems to work as a test bed for undergrad control courses. Thank you very much. I would be happy to take questions.
Unfortunately, we're running out of time, so if you could direct questions after session so that we can keep it.
Okay.
My apologies. The next speaker come up and say.